Number 4, the indefinite integral of 1 over 1 plus e to the x dx. This is not basic form, so the first thing I would probably try is a u sub. If u is equal to that denominator, 1 plus e to the x, the derivative du would equal e to the x dx. I don't have an e to the x, so I know that I'm not really able to do a u sub right now. But remember, what we can do is add or subtract terms in the numerator. So as long as we are adding and subtracting the same thing, then we're really just adding 0 and we're allowed to do that. If we go back to number 4 and we rewrite this and say, well, the problem is I needed an e to the x and I don't have an e to the x. So if I add an e to the x and then subtract an e to the x to that numerator, I haven't really changed the problem, because if you think about it, plus e to the x minus e to the x would cancel and that's just 0. But why is that helpful? Well, it's helpful because we can also then split this up over the numerator, so we're going to be separating the numerator and writing this as the indefinite integral of 1 plus e to the x over 1 plus e to the x minus e to the x over 1 plus e to the x, because I'm allowed to do that. Well, why is that helpful? Well, take a look at that first term, 1 plus e to the x over 1 plus e to the x. If you have the same thing in the numerator and the denominator, that's just going to cancel, and that's just the integral of 1. Now, remember, you can split integration up over addition and subtraction. So I'm just going to call this 1 dx and then minus the indefinite integral of this e to the x over 1 plus e to the x dx. Now this matches the u sub that we tried before. If u is equal to the denominator, 1 plus e to the x, the derivative du would equal e to the x dx, which is perfect. That's what I have. I'm going to bring this guy down. The indefinite integral of 1 dx minus this guy over here becomes 1 over u du. Integrating now, we end up with x minus the natural log of the absolute value of u plus c, getting out of u's and back into x's, we end up with x minus the natural log of the absolute value of 1 plus e to the x plus c. What about number 5? Well, number 5 is not basic form, so I need to deal with it in a different way. I might try a u sub, but the problem is if I let u equal that denominator, 1 plus the cosine of x, the derivative du would be a negative sine of x dx. I don't have a negative sine of x, so I can't be a u sub. Well, what is it that I do have? I have 1 plus the cosine of x. This is trig. Okay, well, I'm going to treat trig a little differently. If you have trig and you have something like 1 plus the cosine of x, you're going to be multiplying by the Pythagorean conjugate and then using a trig identity to get yourself into something that you can integrate. So a conjugate, remember, is same first term, opposite second terms. I'm going to rewrite this as dx over 1 plus the cosine of x, and I'm going to multiply by the conjugate. So the conjugate, remember, is same first term, which is 1, and then opposite second term. Well, the opposite of a plus is a minus. So I'm going to multiply top and bottom by 1 minus the cosine of x. This numerator just becomes 1 minus the cosine of x dx, and the denominator, if we were to FOIL that, would be 1, and then minus cosine of x plus cosine of x would cancel, and then minus cosine squared of x. Now, why is that helpful? Because we now have a Pythagorean identity. Recall, for cosine and sine, we know that cosine squared theta plus sine squared theta is equal to 1. If I were to solve for sine squared theta by moving cosine squared theta to the other side, I know that sine squared theta would equal 1 minus the cosine squared of theta. Well, that means that this guy here, instead of writing 1 minus cosine squared of x for that denominator, I could rewrite that as sine squared x. Because 1 minus the cosine squared of theta is equal to sine squared of theta. Now I'm allowed to split up the numerator over the denominator. So I can put 1 over sine squared minus cosine over sine squared. And we did that just like we did over here, placing each one of the terms in the numerator over that denominator. Well, why is that helpful? Well, now I can use some trig identities. Well, what is 1 over sine squared? Well, 1 over sine squared, that's equivalent to cosecant squared of x. Why is that helpful? Because this here is basic form. But what about cosine of x over sine squared x? Well, isn't that really just the cosine of x over the sine of x times 1 over the sine of x dx? Yeah, of course that is. Well, why is that helpful? Well, that is helpful because cosine over sine becomes cotangent of x, and 1 over sine becomes cosecant of x. And now we have a basic form and another basic form. So the indefinite integral of the cosecant squared of x dx, remember, is negative cotangent of x. And then the indefinite integral of cotangent of x cosecant of x dx is negative cosecant of x. A minus a negative becomes a plus, so in the end we end up with negative cotangent of x plus cosecant of x plus c. Sometimes we're going to need to complete the square to get an integrand that fits into an inverse trig formula. So let's look at number 6 and 7 where we're completing the square. Well, if you look at number 6, it doesn't look like a basic form, but it does have that square root, which makes me think maybe inverse secant or inverse sine. But what's underneath the square root is not a perfect square minus a perfect square, so I know I have to do a little bit of work. I also know a u sub would fail here because if u would equal what's underneath that radical, 8 minus 6x minus x squared, the derivative would be negative 6 minus 2x dx, and goodness knows I don't have that, so I can't be a u sub. Let's complete the square. Now remember, when you complete the square, the first thing you need to do is rewrite it in descending order. So instead of 8 minus 6x minus x squared, we're going to rewrite it as negative x squared minus 6x plus 8. Now we need to factor out the negative from the x terms because the coefficient of x squared must be 1 when we complete the square. We'd end up with x squared plus 6x, and inside of here, remember, we put a plus blank. Don't forget about your plus 8 that comes along for the ride. And then to balance out this expression, we have to put another plus blank. And the reason we're putting a plus is because we're not really adding inside of here. If we take that negative and distribute it to that plus sign, we're really subtracting inside of that parentheses. Now let's complete the square. So the variable is x, and then it's half of the coefficient of the linear term. Half of 6 is 3. And then 3 squared is 9. That's the number that goes into the blanks. 8 plus 9 is equal to 17. We're going to rewrite this so that the positive term comes first, and we're going to write it as 17 minus x plus 3 squared. Now plugging it back into the integral, instead of writing that 8 minus 6x minus x squared, we're going to write 17 minus x plus 3 squared because that is what we get when we complete the square on that trinomial. Well, now we definitely look like inverse sine. We need to identify what is a, and what is u, and what is du. Well, a, remember, is always the number, so a squared is 17, therefore a is the square root of 17. U squared is equal to the variable x plus 3 squared, therefore u would equal the square root of that, x plus 3, and du, the derivative, would equal dx. That's perfect, that's exactly what I have. So we know that this is going to equal the inverse sine of u. Well, u is x plus 3 over a. Well, a is the square root of 17, and then plus c. What about number 7? Well, again, you come over here, doesn't look like basic form, you try a u sub, but the problem with letting that denominator be u the derivative would be 2x plus 2 dx, and I just don't have that. So what I need to do instead is think, okay, well, I have something in the denominator. Maybe it's inverse tangent because of the plus signs and no square root, but let's complete the square just to make sure. Well, we have to write this in descending order. Thankfully, it's already in descending order. I don't have to factor anything out because the coefficient of x squared is already a 1. So I need to just add that blank. Don't forget about your plus 2. And now I have to do the opposite. Well, here I had to add a 9 because really this was subtraction. But since there's no negative out in front here, the opposite of addition is a subtraction. Now we factor. It's x, and then half of 2. Well, half of 2 is 1. And then 1 squared is 1. That's the number that goes into the blanks. Then 2 minus 1 is 1. If we rewrite this, this becomes the indefinite integral of 2. And then instead of writing this guy right here, x squared plus 2x plus 2, we end up with x plus 1 quantity squared plus 1. Now we definitely look like inverse tangent. Our u squared here is the variable x plus 1 squared. Our u then would be x plus 1, and our du would equal dx. Well, I don't have a dx, I have a 2 dx, multiplying both sides by 2, and I get 2 du is equal to 2 dx. A squared would equal the number, which is 1, therefore a is equal to 1. Plugging it into my inverse tangent formula, remember this 2 is a constant multiplier that multiplies along, and then the formula is times 1 over a is 1, times the inverse tangent of u over a, x plus 1 over 1, and then plus c. And finally, I don't need all those over 1s. I clean it up and I get 2 times the inverse tangent of x plus 1 plus c.